Hey guys, welcome back. Today we're going to be talking about the origin of magma. We've been going through the origin of matter in the universe to minerals and how they're constructed from crystals and their compositions, molecules, and so on and so forth. And then we've gone from that to the assemblages of igneous rocks. Now, we haven't actually gotten into the details of where the igneous rocks actually come from. We've just talked about what they are. So in order to do that, we need to discuss magma, which is to say the origin of magma, because it turns out that this is a fascinating field of science all into its own. So without further ado, let's jump right on in. The origin of magma is a highly debated topic in science. Geologists have some difficulty determining exactly how they form. And the reason why is because we don't have the ability to go into the earth and actually look at the melting of the rocks, right? We can do experiments up here on the surface. But for the most part, we have a couple of ways that we can look at it, and they've kind of divided themselves up into camps. We're going to be talking about the non-controversial aspects of it, the stuff that pretty much everybody agrees on. In terms of the formation of magma over time and how it occurs, you might want to take a more advanced course in something called igneous petrology that would discuss these different ideas. But anyway, with that said, let's talk about the non-controversial stuff. All right, so it's generating magma from solid rock. Solid rock is the origin of magma. Remember from the earlier lectures, I've been emphasizing that the mantle is not liquid. The mantle is in fact solid. And all this heat is coming from the mantle, and ultimately, the melting is due to an interaction between the crust and the mantle, and some of that melt makes its way up to the surface. Now, molten rock on planet Earth, it turns out, is kind of the abnormality. The normal conditions for rocks on the Earth is for them to be solid all the way down to the core mantle boundary, where things change a little bit. We'll discuss the core in a later lecture. All right. The kind of melting that occurs is something called partial melting. So not the whole rock melts, just part of it, right? So there isn't oceans and oceans of molten rock in the mantle, but it's mostly, if there's any molten rock, it does come up towards the surface, and we see it in our volcanic chains and things worldwide. So partial melting of rocks in the in the crust and upper mantle. So it comes from pretty far down. It's not generally occurring near the surface. And we need to be aware of the fact that pressure plays a role too. We generally fall into the trap of thinking temperature is everything, but pressure is extremely important. For example, an increase in confining pressure causes an increase in a rock's melting temperature. It's pretty simple. Molten rock, if you put pressure on it, it'll actually lock into a solid phase at a much higher temperature. If you reduce the pressure, the exact opposite happens. Reducing the pressure lowers the melting temperature. That's what we have here in the caption. So if you actually reduce the pressure, it's much easier to melt the rock. And when confining pressures drop, decompression melting occurs. For example, what we see at mid-ocean ridges. Here's a gentleman, this is actually here in Hawaii. He's a volcanologist. He's studying what's going on in this hole. This is clearly molten rock. It's lava. And you'll notice from the orange color, that's the color it glows when it's molten. It's emitting light as a form of its heat energy spectrum. And people get the impression that the mantle of the Earth is this glowing orange color from what we see coming out of our basaltic volcanoes. Actually, the mantle of the Earth is a beautiful green and black color, as far as we know. All right. This, by the way, this feature where there's a lava underneath this rock here, so we have a solid crust of rock up here, and down below here is lava. That's what we call a skylight. And so skylights are actually pretty common in Hawaii and in most places where there's active basalt flows. All right, so decompression melting. This is a figure that we've kind of gone over in previous lectures. We were talking about plate tectonics, and we briefly mentioned ways that you can get melting. But here we can see we got two plates, one moving away from the other, seafloor spreading, and we're making new crust right here in the middle of this rift. And what happens is as you pull the rocks apart, you decompress and you melt this area partially, right? You get a partial melt. You get a little bit more melt up here towards the top, and you get partial melting down here because the pressure is higher. Now, the mantle is believed to be made out of a type of rock called a peridotite, which is basically a largely olivine composition of rock. Remember I said it had that olive green with black speckles in it, the mantle? That's what peridotite looks like. Okay, and so here we see this is actually just a slice of this little system right here, and we get upwelling of mantle rocks, and with the asthenosphere, of course, is that weak sphere that you should be familiar with by this point. And as we see the continents, the plates are spreading one from another, we get this little localized area of melting and a volcanic chain at the mid-ocean ridge. Why does that happen? Right? We haven't really discussed why that happens in detail. We just simply have said that it does. And the reason why that happens is because the Earth has a standard, what we call geothermal gradient. So at any given depth in kilometers here, so 0, 50, 100, 150, 200 kilometers down, and at 200 kilometers you're in the asthenosphere. At any given depth, we can read where the standard geotherm is, what the temperature is at that depth. So for example, 100, we come over to this point, and then we can look straight up and we realize, oh, the geotherm says that the standard rock is going to be about 100, at 100 kilometers is going to be about 1,000 degrees Celsius, right? And the same thing can be said here. What about at 50 kilometers depth? Well, we come over here and then we go up, and that's at about 700. All right, so decompression melting is a really interesting situation. In that case, if you keep the temperature exactly the same, let's say we've got a peridotite that's at 150 kilometers depth, and we decompress it. In other words, we raise it up, but we don't lower the temperature when we do it. We keep the temperature the same. Well, here, it's a peridotite. It's completely solid. But as we move up, we notice that it intersects eventually with this dashed line. And this dashed line says melting curve of dry peridotite. So in other words, once that arrow, once that change crosses that dashed line, we start melting that rock. And that's exactly what decompression melting is basically moving the rock out of a condition off of the geotherm into a zone where melting can begin to occur. Okay, we're going to look at a couple of these as we go through here, and it'll start making sense as we go through several more examples. All right, so in this case, we're talking about temperature as opposed to pressure. So the role of heat, of course, is obvious. Temperature increases within Earth's upper crust, and it's called the geothermal gradient. We just described that. And the average is between 20 and 30 degrees per kilometer. So basically what it means is for every degree, or for every kilometer of depth in the rock that you go, you get 20 to 30 degrees hotter, which means it doesn't take very long for you to go down, say, in a mine, and things start getting really, really hot. Most deep mines, for example, uranium mines in New Mexico or certain other diamond mines in South Africa, they have huge air conditioning units that pipe cold air to very, very low depths within the earth to keep things comfortable for the miners working down there. All right, so rocks in the lower crust and upper mantle are near their melting points. They're not quite there yet, but they're near their melting points. So here we see the geotherm. Right here, here's that melting curve of peridotite. They're not far. Look, if the geotherm happened to be over here, we'd be sitting on a molten ocean, but fortunately we're not. It's just on this side over here. So it turns out any additional heat, and in some cases doesn't require much, from rocks descending into the mantle or rising heat from the mantle plumes, for example, may induce melting. So let's say that for whatever reason you have a mantle plume that starts to affect peridotite that's located on the geotherm here at 150 kilometers depth. You just put a little bit extra heat in here, look, it moves it this direction. You don't even have to change the pressure. Just move the heat over in this direction of the temperature. You'll start melting that rock right at about 1,300 degrees Celsius. Now, if it happens to be up here, let's say at 25 kilometers, you have to add maybe 700 degrees Celsius onto there to go from 500 to say 1,200 degrees Celsius. That's a lot more energy up here, but down here it's not that much. Just a little bit more heat, and you wind up melting that rock. In addition to the liquids that are produced from partial melting peridotite from decompression melting and from increased temperature, you can also change the melting curve. These dashed lines that we've been putting on here are for the dry basalt or the dry curve of peridotite. But we can also put in volatiles, and usually that volatile is water. So roll of volatiles, it's something called a flux. It's something that makes things happen that ordinarily wouldn't happen. So volatiles, primarily water, cause rocks to melt at lower temperatures, right? So you can have a geotherm here, and you don't even have to add heat or change the pressure. If you go and you add a bunch of volatiles, say water, to the rocks, right here, what happens is this melting curve actually moves to the left. And you can see here's the the dry curve, but here's the wet curve. So if you happen to get rocks that are wet, they'll melt at much lower temperatures, and that curve moves this direction. And if you get it within the geotherm, that means that you're going to start melting everything here in the geotherm. So this is really important. This is particularly important where oceanic lithosphere descends into the mantle. And when I say that things are descending into the mantle, you should be thinking of subduction zones immediately. This is actually a really nice parabolic lava flow spurting out of the air, or spurting into the air actually. And the reason why this is happening is because there's volatiles, largely water, which is to say steam, that is acting like a steam jet, and it's pushing the lava basically out into these nice fountains. So that's the origin of lava fountains. Neat stuff, actually. All right, so to understand how magmas change and what they're made out of, remember we have all these different kinds of rocks. We have to understand how these different rocks might evolve from, say, a single melt. Remember, it's all coming from the mantle, the upper mantle, and the lower crust. So a lot of this stuff is coming from the same spot. But up on the surface, they're very different kinds of rocks, right? You get granites, basalts, andesites, diorites, you name them. You know, the whole suite of igneous rocks. They all kind of come from the same batches of magma. So the real question is, why does that happen? Well, we talked about it a little bit in the last video, but let's cover it again. Turns out different minerals form at different temperatures. So at high temperatures, for example, olivine will form at about 1200 degrees Celsius, even a little higher. So olivine will form in this zone here on the temperature scale. And then on the opposite end, down here at about 750, you'll get minerals like potassium feldspar, quartz, and muscovite. So you have to get at colder temperatures to get these to form. And of course, the plagioclase series forms here. Remember that solid solution? Calcium forms at the hotter temperatures and sodium at the cooler temperatures. There's a reason why we spent a little extra time talking about solid solutions, because it turns out they're very important for the evolution of magmas. All right. So a single volcano can extrude, it turns out, different compositions of rocks at different times. Very different compositions. Even here in Hawaii, we see basalt strewn all over the place, but occasionally we get a lava flow that is of a different composition. There's a kind of lava flow not far away from Kona called a trachyte, and the lava flow that came out there is very different than the typical basalts that are all over the rest of the island. It's much thicker, it's much blockier. As a matter of fact, lava flow has several hundred houses on it, and people just think it's a hill, but it's actually a single lava flow that came down. So anyways, how do we get these different compositions to come out of the same volcano? That's my point. That's my main question. And the reason why is we need to understand Bowen's reaction series. So Bowen's reaction series is this. And it turns out that at the highest temperatures, you can get olivine, which is the main component of peridotite and comatite, or the ultramafic rocks. You get mafic rocks when you start seeing olivine and pyroxene. Remember, pyroxene is that black mineral that makes basalt black. You start getting intermediate diorites and andesites when they start to form at these cooler temperatures with amphibole and biotite. And of course, we start seeing the plagioclases in here throughout this whole section. And it's not until we get to the coolest section down here that we start seeing potassium feldspar, muscovite, and quartz. So if a lava, for example, is only allowed to cool to about 1200 degrees Celsius, that means the only thing that we're going to see in terms of crystals that already exist are going to be olivine. Olivine will have been forming for a while before it gets belched out. But If we let it cool down to some lower levels, say 900 degrees Celsius or 850 degrees Celsius, we might see olivine and pyroxene already formed in the magma chamber, but we won't see necessarily amphibole or biotite. And so these things will form in what we call the ground mass. If you recall from the previous lecture, we talked about this concept called ground mass. So the little tiny crystals that surround the big ones, the porphyry. Okay, so understanding that these things come in at different temperatures will help us to explain why magmas create different kinds of rocks. It's very much temperature dependent. All right, so let's demonstrate this by looking at a hypothetical magma chamber. So here's a magma, it has a composition, notice it's this yellow color. And inside that magma, it's cooled enough where a green mineral has already started to form. Okay, so this would be our stage 1 composition, or I'm sorry, our composition A. And what we're going to do is we're going to go to this composition B over time. So as it cools, according to Bowen's reaction series, after we see olivine, we're going to start seeing pyroxenes form in our magma chamber. And these pyroxenes are usually black minerals. And they're going to start crystallizing inside. They're going to start raining out, basically, almost kind of like snow, if you will. They'll be snowing out and growing into larger crystals as they do so. All right, but what does that do? That removes the atoms, the iron and the magnesium that goes into the olivine. It removes the iron and magnesium and the calcium in some cases that go into the pyroxenes. And so what does that do? That changes the composition of the liquid. And it concentrates things like silica and potassium, things that have not yet formed yet, and sodium. All right, by this stage 3 over here, we'll notice that we've evolved it slightly further. We brought in a new species of mineral. In this case, let's assume that it's some type of feldspar, say calcium feldspar or anorthite. And as these form, again, it's evolving the liquid away from having calcium in it, because the calcium is basically raining or snowing out into these crystals. And these crystals are accumulating at the bottom of the magma chamber over time. And finally, once these have all formed, we have a magma with a totally different composition. In fact, if there was an eruption at this time, it might erupt something that is more similar to a granite because it has a lot of quartz or a lot of silicon dioxide in the melt at that point. All right, and so that's basically what we see down here. Let's go through these points. So as we're cooling in this direction from 1200 degrees Celsius to 600 degrees Celsius, notice the crystals get much larger, or I should say the crystal component gets much larger than it is at 1200, and we actually see several species of minerals forming in the magma chamber. So composition changes as a result of removal of elements from earlier forming minerals. Okay, the silica component of the melt becomes enriched as crystallization proceeds, and minerals in the melt can chemically react and change. So it does turn out that as the melt gets more silica rich, it actually becomes a little bit more acidic, and so it will in fact begin reacting with the mafic minerals that are formed in the early part of the crystallization process. So cool stuff. It's something that a lot of igneous petrologists, or what we say, people that study igneous rocks. So a petrologist is somebody who studies rocks. Somebody who studies igneous rocks would be very interested in these processes. All right. So let's review some of the ways that we can go about changing the magma's composition other than just simply having the melt evolve. We'll bring that up. First off, the process where the melt is evolving over time, as we just described in the previous one, is called magmatic differentiation, which is separation of a melt from earlier formed crystals to form a different composition of magma. So magmatic differentiation is a really common way that volcanoes or magma chambers produce very different types of rocks over time. Another thing that can happen is something called assimilation. And I'll have pictures coming up that kind of demonstrate these points as we go forward. So assimilation is changing a magma's composition by the incorporation of foreign matter, such as surrounding rock bodies. That's primarily what does get into a magma, right? So the magma, we usually describe as, there's a pipe in the ground and magma comes out of it. But what it's really doing is it's breaking through rock. And as it's breaking through rock, some of that rock mixes in with the magma and melts. Another way is magma mixing, right? So these magma chambers are not usually in the ground just by themselves. There's usually several in close proximity. If you're in a volcanic area, you might get 3 or 4 volcanoes all being fed through a series of magma chambers that are quite deep in the earth. So magma mixing involves two bodies, it could actually be more than that, but two bodies of magma intruding on one another. And two chemically distinct magmas may produce a composition quite different from either original magma. So if you have a magma that is basically a granite, and you have another magma that is basically a gabbro or a basalt, and they mix, they're not going to form, in theory, they're not going to form a granite or a basalt. They'll form something in the middle, something called a diorite. But that's not always true, but very much so. We'll see compositions that don't match one or the other perfectly, because you got a lot of extra silica in one case, you have a lot of extra iron and magnesium in the other. And how that's going to work out is going to be dependent upon the nature of that specific volcano. So magmatic differentiation is something we've been talking about here. This is a basic diagram. We have a mafic body come in, lots of iron and magnesium. And the first thing that's going to start to crystallize are going to be those olivines, right? Bowen's reaction series. Things that crystallize at 1200 degrees, mainly olivine. You might start seeing the first calcium feldspar shortly thereafter, which is also a mafic feldspar. And it's going to crystallize right around the edges. And over time, you're going to start finding that this mafic edge over here is going to result in a central magma chamber here that is more silicic, which is to say it's going to have more propensity to form quartz and feldspar and muscovite, or become more felsic. And so by the time we get to this stage where there's a late stage eruption or a silica-rich magma eruption, we might have a mafic magma chamber crust or an edge that is solid rock, but the middle part over here might be very much a felsic composition. Okay, so that's how these things evolve, and sometimes they don't erupt at all. If it gets to this point, like what we see in places like Yellowstone, these felsic or silica-rich magmas produce terribly powerful eruptions that cause a lot of damage. They're very, very damaging. If they happen to be a mafic eruption, kind of like what happens in Kilauea, they don't tend to be as dangerous. Fortunately, Kilauea is pumping in so much basalt that it's constantly flooding into here. It's not really crystallizing that much, and it's just going right out the other end of the pipe. So if the magma body is sitting there with any period of time, this will start to happen. Okay. This is an example of assimilation. So here we've got rising magma coming up into rock. This is what we call host rock, right? The liquid has to come up into something solid, or else it's just going to spew all over the surface of the earth. So as long as it's coming up, it's going to be hitting things. And as it comes up, it puts pressure on the sides of the rock. It cracks the rock, and it creates these fissures. And occasionally, rocks break off and fall into the magma chamber, and they melt. And that melting changes the composition of the magma. These broken rocks are said to be stoping, which means it's something that breaks off and kind of floats in. They stope off along these fractures. Okay, and so obviously, if they're of different composition than the magma itself, you're going to get a change in the composition of the magma. And this is an example of magma mixing here. So here we have magma body A, and notice that it's got a more felsic composition. They usually in these pictures, the orangish is the more felsic, and the reddish is usually more mafic. And then when you combine them, you get this mixing, right? These kind of mixing bands. And we actually see these in magma chambers where they flow one into the other. It does some really cool stuff, and sometimes you can get really neat minerals to form in these types of mixing chambers, or mixed magma chambers. All right, so let's talk about how the evolution of magmas results in something called partial melting, right? I've been talking about how it goes to melting. Unlike things like ice, right? You might be confused over how do you partially melt something. Ice, for example, when you get it up to the melting point, which is 0 degrees Celsius, it just melts at 0 degrees. It doesn't melt over a range of temperatures, it just melts at 0. If it's at 3 degrees, ice can't exist at 3 degrees. It has to be water. So this might be a little confusing. The reason why you can have a range of temperatures over which melting occurs is because igneous rocks are not made out of just one mineral. Remember, Bowen's reaction series shows that there are many minerals that form at different times based on temperature, but they also melt at that same corresponding temperature. It's a phase transition, right? So olivine starts forming at 1200 or at about 1250, but it also melts at 1250 if you add temperature or heat to it. So at lower temperatures, you get partial melting of rock for minerals that have lower melting temperatures, such as quartz. All right, so let's show what this diagram has got in here. So we have peridotite. Temperature goes up as we go in this direction. The pressure of depth as we go down is here, and here's our geothermal gradient, right? Remember I showed you how in a previous diagram, typical rock here, you can measure the temperature off here, and notice the temperatures have been removed and the pressure has been removed. This is really just a schematic for your understanding. All right, so here's the normal geothermal gradient. So let's say that we go ahead and create a geothermal gradient from decompression melting. So we have a rock here, it moves up into this zone, a rock here into this zone, and a rock into this zone. And so what that does is that moves the curve, the pressure temperature curve of that geothermal gradient up into this new dashed line here. And notice that it intersects something called the solidus. So this solidus is the beginning of melting of peridotite. So we start seeing the very first melting of rocks, or of the rock, right at this point. And if we get all the way to the liquidus, that means we're 100% liquid. And over here, that means we're 100% solid. Well, notice that there's nice dashed lines going right through the partial melt phase right here, 25%, 50%, 75%. And so in this hypothetical situation, at this depth, say at the bottom of the chart, whatever this pressure or this depth is, we can come over here and we can say, what is that? How much melt am I going to get from moving this into this new geothermal regime? And so you bring it up here and you realize that you might only be melting 10% of the rock. Or anything that is over here that happens to be melting on this translated melting curve would melt at 25%. All right, so incomplete melting of rocks is known as partial melting. So in this case, we'd get 25% of the rock melting down here, up here closer to 10. And that is what results in the formation of basaltic magmas, right? Magmas that are basaltic are not ultramafic, right? They originate from ultramafic rock because only the mafic part comes up, as well as a lot of silica. So it makes it, instead of ultramafic, it makes it mafic. Okay? Most originate from partial melting of ultramafic rock in the mantle, and basaltic magmas form at mid-ocean ridges by decompression melting or at subduction zones. So that tells you something about how subduction zones and decompression melting work, right? Is that we're actually not usually melting the entire rock. Usually we're just melting a small sliver of it. And that is that small sliver that winds up creating the crust. So this is a very important process to understand. All right, so we can have some fun with this. We can use it to explain how we get differentiation of magmas, right? They're all temperature dependent. So we could start partially melting things in light of Bowen's reaction series, and figuring out what might come from it. So for example, the formation of andesitic magmas. So an andesitic magma is an intermediate magma right here. And interactions between mantle-derived basaltic magmas and more silica-rich rocks in the crust generate magma of andesitic composition. So we can blend these two, right? The basalt and the more silica stuff, we get andesite. But andesitic magma may also evolve from magmatic differentiation. So imagine we have a basalt, which is a mafic rock. It's got a lot of calcium plagioclase. It might have some sodium plagioclase. It has all of these things in here, and these as minor constituents. But we take that rock, that basalt, and we melt it. Let's say we bring it up to a temperature, about right here. Let's say at about 1,000 degrees Celsius, maybe 900 degrees Celsius, right around here. In that case, we'll notice that everything that is olivine, pyroxene, and amphibole will not melt because the melting point is higher than that temperature. But the liquid that will form will be from the ions that were in the sodium-rich plagioclase, the biotite, the orthoclase, the muscovite, and the quartz. Well, those are all felsic and intermediate minerals. So the new andesite is going to have a composition that is similar to these minerals down here because these ones are being excluded due to temperature, right? Kind of cool stuff. It turns out that andesite has a plagioclase composition that's right in the middle, right between sodium and the calcium rich, right about here. Same thing can be used to explain granites, right? These most likely form as the end product of crystallization of andesitic magma. So remember, andesites are intermediate. Well, let's take an andesite and we'll melt it just up to maybe 800 degrees, right? We might start seeing only orthoclase, muscovite, quartz, and some of the sodium-rich minerals melting, and the rest of it stays behind. The temperature for melting that is much higher. So the new liquid that is formed from evolving an andesite magma has got a lot more felsic composition. Felsic down here, and as a consequence, we wind up getting a granite. Granitic magmas are higher in silica and therefore more viscous. We talked about viscosity a little bit. That's that tendency of things to be sticky or to not flow than other magmas. And because of their high viscosity, they lose their mobility before reaching the surface. So it turns out that granitic magmas do not flow very easily. They get stuck really easily in the crust, and they very rarely make it up to the surface. And as a consequence, they tend to form these huge plutonic structures. A pluton is a magma body that is buried in the ground, very large structure. And some of these structures can be as big as a mountain. In fact, many mountains are plutons that have been pushed up into the above the surface of the earth so that we can see them. This is actually how we know so much about granites. Again, Bowen's reaction series helps us to understand this relationship very nicely. Okay, so it's really important to understand how these igneous rocks get into the positions that they're in the first place. And to do that, we have to actually bring up some new vocabulary words and start thinking about how they're moving, right? I just brought up, for example, the word Pluton. So let's actually get a definition on what these things are. So most magma is placed at depth in the earth, right? Most of it doesn't make its way to the surface and form a lava. That comes much, much later, and it's very rare. At least on an earth-wide basis at any given time. But there's a huge amount of magma that's underneath the earth, in the earth's crust at any given time. Just very small amounts of it actually make it to the surface. So an underground igneous body, once cooled and solidified, is called a Pluton. All right, so this is where the igneous, the molten rock, comes up like a blister, but doesn't actually make its way to the surface. And they can have different shapes. They can be tabular, which is to say sheet-like, or they can be massive, like a big blob. And they have an orientation with respect to the host rock that is kind of interesting. They're usually discordant, which is to say they cut across sedimentary rock units. We're going to get into what that means a little later on in the class. But discordant means that if there's no sedimentary rock there, or there's no rock there, there's nowhere for the Pluton to come into. Right? So we always find that the Pluton comes in and breaks the rocks above it. That's essentially what that means. It can also be concordant, which is parallel to sedimentary rock units, like a dike. There should be a little space in here, but like a dike, which is a tabular discordant Pluton. So this is where you have rock layers and the magma comes in and it actually injects itself like a blister, almost kind of like a blister between your skin and your hand, if you were to burn your hand, for example. And that blister comes in and separates the skin away from your hand. Magma tends to do the exact same thing in sedimentary rocks. It gets into those layers and it splits the layers and fills in those gaps. Another type of Pluton is a sill, which is a concordant Pluton. We'll show you what these are here in a minute. And of course a laccolith, which is a really interesting structure where the magma comes in and actually lifts the land above it up. Really interesting stuff. So let's look at a diagram that has all of these features in it. So let's start with a laccolith, right? Laccolith is where we get the word lake from. It's the Latin word lac, and it means lake of rock. Lith means rock or stone. So here we see there's a magma chamber. These are actually pretty good diagrams of massive magma chambers down here. And they tend to feed magma up into these sedimentary layers. Usually they're trying to get up for density reasons. If they get stuck down below, it's because the viscosity is too high for them to make it all the way up. and they get stuck and they start feeding these laccoliths. And notice this one came up and it's actually bent the sedimentary rock layers up. Really cool stuff. Here's a magma chamber that's actually formed a volcano over time. This is the pipe. And these fractures in the rock that are feeding lava up higher and away from the magma chamber are called dikes. And these dikes are basically the plumbing of the magma chambers or outside the magma chambers that feed volcanoes and to all kinds of fascinating things. And we were talking about sills. Sills are basically dikes. So notice how dikes actually cut across the rock this way, and will cut across the rock this way. A sill actually gets inside those rock layers and splits it and fills in these areas here. And here's a really good picture of a sill that is out of one of my favorite textbooks. And you'll notice here's the sill. This is actually sedimentary rock, and this layer of igneous rock injected itself right. It's actually right back here as well. Okay, the reason why it's sitting right here on the top of this is because it's harder than the sedimentary rock around it. So all the sedimentary rock around it is washed away and eroded away, except for the sill, which is capping it and kind of protecting the rock beneath it from eroding very rapidly. This is a structure called a mesa, which is a Spanish word meaning table. All right, another really cool thing to understand is how we know about these plutons and how these structures form and whatever. Most of our ideas come from analysis of batholiths. So a batholith is a whole bunch of plutons. So in this case, we got a batholith here. Look at all these plutons. They're all mixed together. They've all come up over time and cut across each other and sit through each other. And this series of batholiths here now form a mountain range. And the reason why they form a mountain range is because granites and andesites and things like this are much less erosive than the sedimentary rocks or the metamorphic rocks or whatever kind of rocks that usually the granites come into. The granites are usually fresh, they've got good strong crystals, and they're going to last a lot longer. So they can survive the weathering environment much better. So when all things are being washed around, say off of these rocks, we can see that these peaks form and they expose these once buried plutons to the surface. And this is very similar to what we see in the Sierra Nevada of California. So if you ever get the chance, you want to do some beautiful hiking, go to the Sierra Nevada and you'll see some beautiful plutonic rocks and some other really great rocks as well, not just plutons, but that's where we know a lot of our plutonic petrology from. So it turns out that many igneous mineral resources can form from magmatic segregation, which is the separation of heavy minerals that crystallize early or enrichment of rare elements in the residual melt. So residual means last stage, the very last thing to crystallize. Hydrothermal solutions, which is hot water, because it turns out there's a lot of water in these magma chambers. These originate from hot, metal-rich fluids that are remnants of the late-stage magmatic processes. And remember, magma wants to form things like granite, and there's not really any place for things like water to go. So the one thing that magma chambers do a very good job of is injecting that water into the host rock around it. It doesn't necessarily want to hold it into the magma chamber. And as a consequence, we have, say, a fault, which is a break in the earth, and this water will escape along here. And not just the water, but it will take a lot of metal fluids, or metal-rich fluids like gold or silver or copper. And these metal deposits are usually found right adjacent to the magma chamber. So if you find a nice granite and you find some host rock, this is usually a good place to start looking for metals. And in fact, in California and many places in South America, prospectors go out and make claims exactly on the area where the magma chambers or the plutons touch the country rock or the host rock. Really neat stuff. There's a lot of minerals that have been pulled out that way, not just gold, and silver and copper, which are very important, but nickel and arsenic and mercury and uranium in some cases. These can all be found in these types of deposits. All right, so we do need to correlate igneous rocks to plate tectonics. We want to make sure that we can validate our plate tectonic theory, and so far we've been able to do so. The best way to look at this, and probably the most selective way of doing this, is looking at what we assign now as the Pacific Plate, which comes through here, is kind of buried under the ocean. Unfortunately, these volcanoes, which are these red spots on the Earth, um, are all above ground. So we don't actually get to see the undersea volcanoes. But this is the edge of the Pacific Plate. And we'll notice that even in California, down into southern Mexico and into western, well, actually, it goes over here, the Pacific Plate does, but there's a plate edge over here called the Nazca Plate. It validates our ideas about plate tectonics. So it turns out that the origin of magma is very closely tied to plate tectonics and the plate tectonic interactions. So if you don't understand the difference between a convergent and a divergent and a transform margin and how that might result in the formation of magma, you should probably go back and review some of the earlier videos so that you have a clear understanding of the plate tectonic processes that occur there. For example, here we see that in the Western Pacific, this is actually all subduction zone here, so we would expect to find volcanoes. But look over here, we have something different happening. Here through Ethiopia, this is the Afar Rift, and we see tons of volcanoes in here. And the reason why is essentially this little sliver of Africa is rifting away from the main part of Africa and joining the Indian Plate, which is located over here in the Indian Ocean. Madagascar has already made that change. This is the island of Madagascar. So this validates the rifting hypothesis, which we see with other evidence as well, all of these volcanoes from decompression melting. All right, so that's a lot of information. You might want to watch this video more than once if some of it's confusing, especially the idea of the evolution of magmas and the fluids over time in a magma chamber, how a single volcano, for example, can produce different kinds of magma. If you have any questions, feel free to send me an email or message me on the discussion board.